Okay, so now we have a very exciting keynote speech by Laurent and Ghaoui. So Laurent is a CNRS bronze medal recipient. He got his PhD in aeronautics and astronautics from Stanford in 1990. He's now a professor here at Berkeley in the computer science department. He's also part of the Berkeley Artificial Intelligence Lab, and he's also the founder of 2 startups. So Summit Analytics that does text analytics for business applications, and then Keros that does satellite imagery analytics for energy markets. So please join me in welcoming Laurent. I'm very happy to have you here.
Thank you so much. Thank you. So thank you for inviting me, and you know, it's hard to do a guided tour. And I realize that there's already a lot of expertise in the room, so I apologize in advance if you find it boring. What I want to delineate today is both the promise and also point to different tasks that we can think about when it comes to interacting with text. And I'll do a little dive on technology. I know you like to see math formulae. So you'll have your share, and then at the end I want to outline some challenges. So essentially, you know, it's a very exciting time. A lot of progress, in no small part to the brains at Google and elsewhere, who sit on a lot of data to produce these wonderful models. But I really feel, and I think you are in sync with that, there's a lot of progress to be made, and maybe on the technology frontier, but also on the interaction between traditional content analysis and these new models. So I think we all agree that this should not be seen as a replacement. We're not going to chatbot sociology and humanities away, but hopefully we can empower it. So this quote here is just to illustrate how subtle text can be, and it's extremely hard to actually go to the truth of text. And I don't think there is any commonly accepted truth of any text. So I think these automation tools can help us guide, and we should lower our bar in that regard. So this is a long laundry list, but you have seen a lot of topic modeling. I do believe that this is a very important thing. Word embeddings are also very popular, but there's a host of other things that are available. Let me just point out, like, for example, outlier detection. Just show me in all these police reports those who stand out. And what does it mean even? But you know, try to help me find what's not the norm in that data set. There is also something that I really like, and it's called sometimes exemplar extraction. It's a task which is really about summarizing text, but by extracting documents. And so, you know, we all know about topics, right? This is a machine that will extract keywords, and you know, depending on how we represent text, it may come in the form of unigrams. If you do this on a large corpus of New York Times, you recover topics that you know, you expect. So, and this comes into leads us to really know, well, if I know this, what is the use? And if I don't know, what is the truth about it? So, you know, there's always that type of quandary. But from the modeling side, from the technology side, topic modeling is not a solved problem. I mean, there are good techniques to do this, but I expect this field to continue to be producing new, better algorithms and so on. And I'll try to delineate what are the dimensions of that search. You can apply those in many contexts. So in the top study here, and I apologize, you can't probably see, but what's going on is basically we do principal component analysis with a few spice in there to extract keywords, and the data set shown up there is a pilot report data set. So when you fly, if there's an incident, the pilots, they have the right to anonymously submit a report on the incident, and it's filed and curated, maintained by NASA. And it's a treasure trove of, you know, real life, workplace type of issues. And then you can have fun with trying to analyze what's going on at different airports, what are the main issues that talk about. The graph doesn't show the entire data set, only the runway related incidents, what happens when the plane is on the ground. If you do the whole data set and you extract the main topic, you might be interested in knowing what is the main topics that pilot reports about. So I'll give you the topics, the topic in the form of a short list. It's first class, passenger, alcohol, flight attendant, police. That's the first topic. Once you have a good topic model, good or bad, who knows what that is, but once you're confident about your topic model, you can start doing time analysis, as we've seen recently, and you can analyze, for example, a slice of time or the evolution of a topic over time. You can go back and forth to data. What I notice oftentimes is that topic modeling being only the first step, you want to then extract the documents that exemplify, contextualize your topic. So you can see an example and check. For example, sometimes we see topics in a keyword, for example, chubbier. It'd be nice if you could click on chubbier and show me the main examples. That's an exemplar selection problem. So you see there's a whole pipeline that we should expect. This is still about the pilot data and trying to dive into a topic. So when we talk about topics, there's a very natural notion of subtopics, right? But it's not trivial because what data set do you use to find that subtopic? So it means that you first identify a topic, and then in this case, we're looking at all the pilot reports from a particular airport at Dallas. And the first line of keywords, and you might not recognize them, this is jargon. This is in, pilot jargon. They talk about runways, taxiways, and all sorts of things. That first layer of topic analysis, then you want to go beyond and see, well, let me explore this keyword and see what are. So once you start thinking about topics as an object of study, you need to have a method to group all the documents that really talk about the topic. And that's not a solved matter. I mean, many documents, especially if they're long, will contain more than one topic. So the other part that I want to mention that's not so obvious is that in this field, there's a lot of emphasis on for example, going back to word embeddings that you heard about yesterday, it's all about similarities between words. It's a wonderful tool. However, you must think about, well, once I have that similarity and I want to compare, like I want to find this word and the closest words. If I adopt a pairwise approach, then you might run into a problem that I call the minority opinion problem. So I try to picture this geometrically with this little pictogram, but essentially you have a query and you do some pairwise comparison to find similar documents or words. If there's a lot of the same type of words or documents that are close to your query and you decide, okay, I'm going to just look at the top 10 or 100, you might be swamped by one cluster. Type mining into a search engine. The first 100 pages will be mostly about mining minerals. And sometimes you have mining bitcoins. You don't even have data mining anymore. It's passé. Who does data mining? But you see that's what I mean. You need to have a similarity analysis that identifies the clusters and provides you with the examples of which. And maybe you will serve to the user, if the cluster is big, you serve more than one example. The other, so in the exemplar extraction technique, what you really look for is the concept of spanning conversations. So you want to extract things that are, or documents in this case, that are representative in the sense that there's a lot of neighboring documents attached to it. So basically it's like topic extraction, but not without referring to keywords, just raw documents. In this analysis, you can find that it seems if you run this kind of algorithm, you do identify what you expect. And again, this points to, okay, what as a user do I expect? Is this just going to validate my findings, or am I going to discover new things? And it's always a difficult question. So in terms of the technology, I'm just listing what I know about. This is really a vibrant field. And just to take a little step back, from what I've seen, I've been involved in that field since about 2007. At first I thought, oh, it's problem solved. Like I naively thought, okay, the main task is search. We search, and Google search, for example, is a wonderful thing that works. So what is more to see? And around that time, until maybe 2010, most of the approaches were relying on variants of pretty standard, by standard I mean like classical techniques. So principal component analysis is one of them, and topic models are more or less a variant of those. There's ones that are very fast, those that are slower, as we saw when a previous speaker referred to hours of computing time. But at the end of the day, they fall in that same category of models that actually, strangely enough, originated in the field of sociology. PCA is a sociology technique. It was invented by sociologists. But then you have more complex models like word embeddings, and I'll try to briefly mention them. Sparse optimization is something that is, I wouldn't say it's an established technique in the field of text analytics. I really like it. I find it's powerful. So just a little word about what that is. It's just about discovering, it's a signal processing technique. It's about, in a bunch of signals, trying to extract the main features that you can use to reconstruct the whole database of. So typically it was used in, as I say, in signal processing of time series. It's a very geeky type of thing. And I believe that text analytics is one of these data fields, right? It's a data science. I mean, you can say it that way. And for a computer, just seeing an array of numbers, you can apply any technique of signal processing. And those techniques, they have that element that I wanted to allude to in this particular case, for example, where you're trying to extract, say, documents, okay, that are examples. Based on a query, you want to find neighbor documents. If you don't have a budget and you say, well, extract as many documents as you want, and then as an afterthought, if you have a pairwise comparison approach, you can rank all the documents and then select the top 10. And so the selection of a few documents is done at the end of the process, of the algorithmic process to rank the documents. So the ranking doesn't know you're going to cut it short. And so it believes that it has all the budget in terms of how many documents it can recommend you. And that's what search engines do. When you type mining, you get 100,000 billion results because Google doesn't know or doesn't want to know that you're going to look at the first page. But if I tell you, oh, no, you're going to only look at the first page in your results, well, just then you have to be cognizant of that, and the algorithm should be modified to show you, 5 things about mining minerals, 2 things about mining Bitcoin, 1 thing about mining data, and so on. So sparse optimization, to me, is a layer that you can put on many different algorithms, And I think it's an interesting technique. So because this is supposed to be a guided tour, let me just briefly discuss some of these elements. And again, I apologize because many of you know that by heart. You've been using it and producing results with it. But the very first step is to represent text. And so in that choice, or rather in that step, you have so many choices and none of them really necessarily dominates others. In the previous talk, you've seen topics rendered as stems, that is single words, but that are cut to their essential stem. That's an approach where you look at the occurrence of these stems, like customers would be in the same group and represented by the same feature or token. And so there's many design choices here. We usually refer to this as, processing, pre-processing. You're just massaging the data. So what do you want at the end? Is really an array of number, where rows might represent documents and columns might represent the features. And those features might be, okay, appearance of this and that word, excluding those stop words, because stop words, if the algorithm is not smart enough, these are words that are very common, not necessarily informative. Ideally, you would want to make as few choices as possible at that level. You would want to let the algorithm discover, oh, you should use unigrams, single words, or consecutive words, bigrams, or n-grams. It should be data-driven, but that holy grail is far from being the reality. And the last thing I want to mention about representation of text is that at the end of the day, it sends you to a geometric space. It invites mathematics and mostly, linear algebra or nonlinear algebra, non-Euclidean, but essentially, it's an intriguing device for, I would think, a social scientist, because it becomes seemingly impartial. You're now in a totally different way of reasoning. You don't bring in your biases, except, of course, in the choice of stop words, for example. So, so what are topics in that space? We're dealing now with points. And of course, I show here a bunch of points. This is a cloud of points. And each point is a document. And it's now represented by 3 coordinates, depending on how many words of the type 1, 2, and 3 I find in the document. Of course, in practice, you might have 100,000 dimensions. And you might have 1,000,000 points. And so this is very hard to conceptualize. And topics in that space, there are really directions. So what do I mean by directions? It's just like the ordinary notion of a line. Why do I call this a topic? Because simply imagine a document that contains the same tweet over and over again, exactly the same tweet. Then all the points would land on the same place. Instead, let's take one tweet that has a word pattern, and then another maybe longer document that has other words. So you can see that the points will not be exactly at the same location, but they will be essentially close to being on a line. And that's why we call this a topic. That's a connection to linear algebra, essentially. And based on that, you can then take a data set and see how many topics you have in the data set. Why is that? Because you can geometrically understand if a cloud of points is made up of a few lines or not. And you can measure the error. That's really something that was referred to in a previous talk as explained variance. It's basically how well your model fits the available data. And it turns out that, strangely enough, when you do even a cursory analysis, you find that modern data sets from text are often extremely low rank. They can be explained by just a few topics, okay? So this is a poor man's version of what I'm trying to say. What I'm showing here is a curve that shows the strength of topics, or a proxy for it, on a real life, 300,000 document data set. So very quickly the number of topics is exhausted. That doesn't mean the word usage of the words is always the same and so on, but these important words serving as topic, there's only a few of them. Now an interesting aspect of text analytics is that there is often a distinction between unsupervised learning and supervised learning. What do we mean by this? Supervised learning is when you provide the computer with examples of some outcome. Like, let's say, for example, you want to predict using image data from MRI plus clinical records, you want to predict an outcome. So you might think, let's use a predictive model to take those images, send them into this high-dimensional geometrical space. We don't even know how it looks like. And then we do the same with text. So all data is the same in the sense that you can mix text and images to predict whether, to predict outcomes. So make better diagnosis based on the clinical records and so on. So predictive models can use text analytics, and usually brings you a new way of looking at things that is very informative. But you can also use prediction as an excuse, and that's at the basis of word embeddings. I'll come to that later, but here in this analysis here, what we've done is looked at, so these are PubMed abstracts. There's a lot of them. These are short documents, paragraphs. It's an abstract of scientific papers. And if you look at different predetermined categories, because there's the metadata associated with these abstracts, you can say what's the image in PubMed of arthritis, okay? What's the image, and I'm sorry, I can see it's hard to read, but basically these are different diseases and keywords associated with them. And what you can do is take prediction as just an excuse or as a device by which you identify those keywords. So approach one, you take a disease and you analyze the topics. That gives you topics. Or you can use, try to make a prediction. If I did not know the category of this abstract, could a computer model predict to me the class or the disease that this abstract is talking about? I'm not caring about this prediction task. All I want is to identify the important feature in that task. So if you use sparse optimization combined with prediction, you will have a budget for a few words that really characterize the appertinence to a disease category. And that way you'll identify keywords that belong to this category. So if all these papers, they all talk about, say, medicine, then medicine on a topic analysis will emerge as a keyword for each one of these categories. But we can see that medicine is not predictive of a particular disease. So by having a budget of a few keywords to identify and doing this comparative analysis, constructing analysis, we can come up with words that are pretty well matching the targets. So in word embeddings, and I know I couldn't attend, unfortunately, yesterday, but I think you had an exposition in several talks about that. But just to recap, word embeddings, they use prediction as an excuse. It's really an unsupervised approach, so you don't have to train your model, you don't have to have human labelers telling you what it is, or know the outcome of a graduate student or a student admission college essay. You take your raw data and you set up your own prediction task, and because you have the answer in the data, that's your training. And basically it's based on a sliding window approach, trying to predict based on context words that are nearby, what is the word in red. So you essentially set up, it's a fake problem, uh, and hopefully not a fake news problem, but it's a fake problem where you actually try to predict based on the blue words what is the word that is in red. Okay? So on one hand, you put the outcomes, which are the red words, and on the other hand, you put the blue words in two different matrices or arrays. If you do this on a sliding window, you can see how big the problem quickly becomes, because you're going to try to predict each word. So in a sliding horizon fashion, each data point is a snippet of your text that you slide, and so it becomes very big. The other thing that is important to realize is that your data set has to be big also to show many examples, because you're going to make a prediction what's in the red here. If this is a choice among all the words in your dictionary. So they call it a multi-class problem, where the multi refers to how many words you have total. So it's really a giant problem that is challenging on many levels. And this is my one formula that I would like you to get a grasp on. So essentially, at the end of the day, it's something that you can think of it mathematically. And what it does is this. It tries to match the target, which is an array that tells you which word is where, to the context, which is another array that gives you the blue words. So you can think of Y, this matrix, as the red words, and the X as the blue words. And in between, you have a matrix of coefficients. If you have no constraints and you're just trying to match it, this is a pretty standard yet very large-scale problem. If on top of it you want to compress the coefficients so as to be able to kind of interpret them, then you have a constraint problem that's not easy either, but with enough time on your hands, you can solve that. By the way, modern technology can solve this pretty fast. I mean, there's implementations that are pretty fast, so it's not like many hours. At the end of the day, this is just a variant of principal component analysis or different techniques. There's different ways to look at it, but it's not like revolutionary. I think what is revolutionary is twofold. The first is the model setup, the idea of using prediction as a way to understand text. And the other is essentially the presence of data and the availability of data. So let me wrap up, and I think I'm going, yeah, okay. So I know we're all hungry, so I'll just wrap up two last slides. I want to mention that text analytics is wonderful because it will never be solved, so we'll always have business in there. But the idea of metrics is an important one, but again, it's an intractable problem. Nobody's gonna, we can always challenge the quality of topics and always ask, why these topics, why not these others? There's metrics and there's also qualitative assessments, but it's an open problem. The other part that to me is like maybe less conscious on the radar is essentially what goes on in users' minds. So I think all of you're here, meaning you demonstrate already a strong interest in text analytics, so you don't need to be convinced. But there's out there a lot of people who are really not convinced about it. And I think, of course, the work that's been shown, here's a case study on college essay, here's a case study on police reports, and so on and so forth. That is a great help to see how you can use those tools in the flow of a reflection. But what are you competing against is the idea that search engines solve the problem. That you don't need any text analytics, you just go to Google and you have all the answers. You may laugh about it, but it's something that I found personally to be present when I try to convert people. And of course, there's this idea that in web search engines, you don't even rely on your own data. so you don't know what's going on. It's absolutely not transparent. But, okay, don't get me wrong, it's a great step, but we need to move on. Also I want to insist on speed. So this afternoon, my colleagues at that startup, they will present you with a tool that I think could be relevant to, it's supposed to be, it's very fast, you don't have to wait hours at all. But why is it important to have a speed there? I think it's important because it needs to be a conversation. You need to be able to ask questions and get the answers quickly because you form hypotheses. What if, I use this subset of data where I only look at the responses from citizens to police officers? What is in there? If I have to wait or code Python to just get my data, and it's a very long process that I'm sure we all encountered that problem of just getting there. So I think speed is a super important aspect of any algorithm. That's why I think search engines are popular. If you had to wait 5 minutes for each one of your queries, I don't think you would use search engine as much. Even 5 minutes. What about 44 hours? It's like mind-boggling. So it's important to have technology that is robust, as transparent as possible, but also extremely fast. Because at the end of the day, text analytics is not solved and will not be solved anytime soon. Thank you.